and welcome back to Teacher Gimbel's channel. Today we're going to be going over Algebra 2, Unit 1, Lesson 6 Practice. If you like this video, make sure to like and subscribe, I'm pretty sure by hitting the button over there, and I'm looking forward to seeing you in other videos. Let's get started. Problem 1. An arithmetic sequence A starts with 2, 5, ... Write a recursive definition for the sequence using function notation. So there's a few things we need to remember. First off, when we talk about n, we're talking about the terms of our sequence. So n equal 1 will be the first term, n equals 2 equals the second term. The first, second, and third, that's not exactly correct notations. It should be 1, 2, and 3, but I like to think about it like that to make it a little bit easier, because notation is half the problem. A of n is equal to the value of the nth term of our sequence. So if I say a parentheses 5, that means what's the value of the fifth term of our sequence? And then here, a to the n minus 1, which we're going to see a whole lot, is equal to the value of the previous term. So if I say, if I have two terms in my sequence and I want the third term, and it had a to the n minus 1 in it, it would be referencing take the second term and do something to it. But it's a lot easier in practice than it is in theory. I just like to spell these things out because the notation is harder than the math in this case. And so being good with the notation is going to help us be better with the mathematics. So write a recursive function for this sequence using function notation. So we start at 2. That tells me that a to the 1 is equal to 2 because the first value in my sequence is 2. Now, using this information, I want to say what is a formula for the rest of the values in the sequence. So I want a formula for any value. Well, if I start with 2, I can see that I added 3. It's just going to be the value of the previous number plus 3. And we're done. So if we want any term in our sequence, it's the value of our previous number plus 3. And we always will have a previous number as long as we start with the first one, because we just keep adding 3, adding 3, adding 3. 2. Use your definition to make a table of values for a to the n and find a to the 6. So I'm going to make a very tiny table of values over here. And we're going to start with a to the 1, which we already know is 2, a to the 2, which we know is 5, a to the 3, a to the 4, a to the 5, a of 6. I'm saying to the, which is not quite correct notation, but it's a of 3, a of 4, a of 5, a of 6. So our third term is going to be the previous term, which is 5, plus 3. So that's going to be 8. Our fourth term is the previous term, which is 8 plus 3, which is 11. 11 plus 3 is 14. 14 plus 3 is 17. And there we go. A to the 6 is equal to 17. And we're done. So the more you practice, the more you see that this is actually way more straightforward than you realize. So let's go ahead and erase all of this so we can go on to the next question, but keep our notes where we want them to be. Problem 2. A geometric sequence starts with 1, 3. So I'm immediately noticing that I'm multiplying by 3, and I know it's multiplying by 3 because it's a geometric sequence. Let's use dot 3. Write a recursive function for this sequence using function notation. So again, we're going to say we know our first term is 1, and our every other term is going to be the previous term multiplied by 1. And we're done. Sketch a graph for the first 5 terms of G. Well, now that we're expert at finding the terms, let's quickly go ahead and figure this out. We have 1, we have 3, multiplied by 3 is going to be 9, 27, 81. Now we want to create a little graph for it. Let's go ahead and create our table of functions. We're going to say this is 20, 30, 4, no, I did not want to do that. I wanted to do 20, 40, 80. 40, 80, and because this is a sketch, it's all right. And we're going to go each of our terms. So our first term, our second term, our third term, our fourth term, and our fifth term. So our first term is 1, very tiny. Our second term is 3, still tiny. 9 is going to go about halfway up. 27 is going to go over here, and our fifth term is going to go all the way up over there. And there's our graph. Here we have term, and this is going to be the value of whatever term that is in our sequence. Notice it's a geometric graph, which makes it a curvy graph. Explain how to use the recursive definition to determine G of 30. don't actually determine g of 30 of this value? Well, in this case, to determine g of 30, we're going to have to use our function and literally multiply by 3 30 times. Why do I have multiplied by 1? Look, I typed that down wrong. We all make mistakes. Definitely be careful about making mistakes. Multiplied by 3. What I would do is I would go back to our lesson 4 video, and if you don't know how to do this, use an Excel spreadsheet, type in the first few values, drag it down, and then you'll get to g of 30 real fast. But a recursive function is repeating a rule, and in this case, it's based on our first value of our function, so we just have to do it 30 times to get to the 30th value. We are not going to do that. But let's go on to the next question. Problem 3. Match each sequence with one of the recursive definitions. Note that only part of the definition showing the relationship between the current term and the previous term is given, so as to not give away the solutions. So let's go ahead and look at this. I'm going to quickly note that this is geo and this is geo. This is because they are multiplied. I see that we have the previous term is multiplied by 1/3, the previous term is multiplied by 5. If it's multiplied by 1/3, it means he's going to be getting smaller and smaller. I'm going to look at my answers and I'm going to say, which ones are getting smaller? This is getting bigger, this is getting smaller, and this one's getting smaller. This one looks like I think it's the correct answer, so let's double check it. 6 is a term we have, so we're going to call 6 is going to be our a to the n, should equal 1/3 times the previous term, which is 18. This is correct. Let's double check it with another number, but I think we found the correct function. So 2 should equal 1/3 times our previous term, which is 6. Also correct. So we're going to say b is equal to 1. We've matched it. Now let's see what else we think might be a geometric function. Well, this guy seems to be getting bigger in a geometric way, so let's double check it. I'm going to choose 75. Should be equal to 5 times the previous term, which is 15. That's correct. Now we've got to figure out these two. This one's going to be minusing 4. This is adding n minus 1, which is the place value of the previous term. So let's quickly do this one before we jump into this one. This is going to be minusing 4. I see that this one is minusing 4 from each term. I'm going to check a term in the previous term, so the term should equal the previous term minus 4. That checks out. I've matched it. So when we're doing these questions, we want to use the process of elimination to work smart and not hard. Now let's check this dude over here. Let's take the 7. 7 should be equal to the previous term plus what place value the previous term is. So the place value of the previous term is 3. That works. And we're done. Now, if you remember, I said n minus 1 represents, well, we actually defined a as n minus 1, which is the value of the previous term, but n is going to be the term you have, and then n minus 1 equals the place value of the previous term. All right, so n and n minus 1 are notation that you should be learning and that you should kind of begin to intuit as you do problems like this, because if you don't understand it, these kinds of questions start to look really scary really fast. All right, problem number 4. We only have 6 problems here. Write the first 5 terms of each sequence. All right, let's get started. Now, based on the last lesson, our intuition about this should be getting a little bit better. So hopefully this becomes easier to us. So our first term is 1. Our next term is going to be 3 times the previous term. That's going to be 3 times the previous term, 3 times the previous term, 3 times the previous term, and we're done. For B, our first term is 1. Our next term is -2 plus the previous term. So -2 plus the previous term is going to be -1, -3, -5, -7. I can't write today. -7, and we're done. For 3, our sequence C, again, starts with 1. And it's going to be 2 times the previous term plus 1. So we got to be a little bit more careful here. 2 times 1 is 2, plus 1 is 3. The next term is going to be 2 times the previous term, which is 6, plus 1 is 7. The next term is going to be 2 times 7, which is 14, plus 1, which is 15. The next term is going to be 2 times 15, which is 30, plus 1, which is 31. And we're done. For sequence D, we start with 1. Now, this is going to be, this notation I'm uncomfortable with, and I'm going to do a side note right over here. D to the n minus 1 squared. I'm not sure if this is like D to the n minus 1 squared, where it's like the n minus 1 squared, or if it's D to the n minus 1, the whole term squared. In this case, I'm going to be assuming it's this guy right here. But that notation's pretty tricky, so make sure when you are ever in a place like this, just put an extra parentheses so you don't make this mistake. So our first term is 1. Our next term is going to be the previous term squared, so 1 squared is 1 plus 1, which is 2. Our next term is the previous term squared, so 2 squared is 4 plus 1 is 5. This term is going to be the previous term squared, so 5 squared, which is 25 plus 1, which is 26. And this term over here is going to be 26 squared plus 1, which I cannot do off the top of my head. And you put that in a calculator and you'll get your answer. All right, last one. F. Well, our first term is 1. Then we have the previous term plus 2n minus 2. So I'm going to go over here and I'm going to put down my n values for each term. So this is going to be my first term. This is going to be my second, my third, my fourth, my fifth, my sixth. And is going to equal these guys down here. And that's just going to help me do some calculations. So we have our first term, which is 1, plus our 2 times n, which is 4, minus 2. So we're going to have 1 plus 2 times 2 minus 2, which is 1 plus 4 minus 2, which is 3. Let's do it again. So the next term we're going to have is going to be the previous term, which is 3, plus 2 times whatever number term this is, which is also 3, minus 2, which is 3 plus 6 minus 2, which is 7. And again, the previous term is 7, plus 2 times the current term we're on, which is 4, minus 2, which is 7 plus 8 minus 2, which is 13. Let's do it 2 more times. And again, the previous term, in this case, well, that was 13. The previous term is 13, plus 2 times a place value, which is 5, minus 2. So it's 13 plus 10 minus 2, which gets us 21. Now, the last one, and there is a pattern here, which if you notice, good for you. But we're going to keep using our function because we like functions. It's the previous term, which is 21, plus 2 times a place value, which is 6, minus 2, which is 21, plus 12, minus 2, which is going to get us 31. And we're done. All right, so if you can intuit what the notation means, these questions end up being quite easy. If you need a second to pause to redo what I did or to think about it, take a second to pause as we move on to question number 5. A sequence has f of 1 is equal to 120 and f of 2 is equal to 60. So I know it's a sequence. I know my first term is 20. I know my second term is 60. Determine the next 2 terms if it's an arithmetic sequence, and then write a recursive definition that matches the sequence in the form. Well, if it's arithmetic, it means it's changing by a constant amount that's added or subtracted. So we subtracted 60. So we're going to keep subtracting 60 to get our term. Now we have to write a recursive function that matches the sequence. So if f of n is 1, f of 1 is 120, we know that. F of n is going to be the previous term plus minus 60. And we're done. Now determine the next 2 terms if it's a geometric sequence, and then write a recursive function. Okay, well, we've done this. This is good practice now. So if we have 120 to 60, that's a geometric. I see that I'm multiplying by 1/2, which is going to give me 30, 15, 7.5, ... So if our first term is 120, then each other term is going to be 1/2 multiplied by the previous term. And we're done. All right, let's go on to our last question. Problem number 6. Oh, this one has a table. My face is in the way of the table. Let's move my face. 1 hour after an antibiotic is administered to a population, 1 hour after an antibiotic is administered, a bacterial population is 1,000,000. Each following hour, it decreases by a factor of 1/2. Complete the table with the bacterial population at the given times. Does the bacterial population make a geometric sequence? Explain how you know. Okay, well, this is 1,000,000, and which means after 2 hours, it's going to be 500,000. This is why we take vaccines. After 3 hours, it's going to be 250,000. After 4 hours, it's going to be 175,000. After 5 hours, it's going to be 175,000 divided by 2, because what I'm noticing here is each time I'm taking the previous term and I'm just multiplying it by 1/2. Multiplication and division are cousins, so multiplying by 1/2 is the same thing as dividing by 2. So whichever one you're more comfortable with, as long as you understand the relationship between multiplication and division, you can use in this problem. So this is going to be 8750. Do your mental math or use your handy dandy calculator. I always recommend using a handy dandy calculator because don't waste your time doing mental math. And is a bacterial population make a geometric sequence? Yes, it does. Because we know that there is a constant value which we multiply each of the previous terms by. This value is 1/2, which gives us a geometric sequence. All right, if you have any questions, please go ahead and put them in the comments, and like and subscribe if you like this. I'm looking forward to seeing you next time.